Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The holographic cosmos. Are we living in a 2D projection? The holographic principle is one of the most mind-bending ideas in modern theoretical physics. At its core, it suggests that all the information contained within our three-dimensional universe might actually be encoded on a two-dimensional surface, much like a hologram. This concept, which stems from attempts to understand black holes and the nature of gravity, challenges our fundamental perceptions of reality and has profound implications for our understanding of the cosmos. In this narrative, we will explore the origins, development, and potential implications of the holographic principle, and consider the tantalizing possibility that our universe could be a 2D projection. The seeds of the holographic principle were planted in the 1970s when physicists began to grapple with the mysteries of black holes. Black holes are regions of space where gravity is so intense that not even light can escape. They form when massive stars collapse under their own gravity, creating singularities where the known laws of physics break down. One of the most perplexing aspects of black holes is the information paradox, a problem that arose from the work of physicist Stephen Hawking. In 1974, Hawking proposed that black holes are not entirely black but emit radiation due to quantum effects near their event horizons, the boundaries beyond which nothing can escape. This radiation, now known as Hawking radiation, leads to the gradual evaporation of black holes over time. However, this posed a significant problem. If black holes can evaporate completely, what happens to the information about the matter that fell into them? According to the principles of quantum mechanics, information cannot be destroyed. Yet, if a black hole evaporates entirely, it seems that the information contained within it would be lost forever, violating a fundamental tenet of physics. This paradox led physicists to reconsider their understanding of black holes and information. In the mid-1990s, theoretical physicist Leonard Susskind and Nobel laureate Gerard T. Hooft proposed a radical solution to the problem: the holographic principle. They suggested that all the information that falls into a black hole is not lost but rather encoded on its event horizon, a two-dimensional surface surrounding the black hole. This idea was inspired by the work of Jacob Bekenstein, who had earlier shown that the entropy, a measure of information, of a black hole is proportional to the area of its event horizon, not its volume. The holographic principle posits that the maximum amount of information that can be contained within a given volume of space is proportional to the surface area of that volume, not its volume itself. In other words, the three-dimensional world we perceive may be a projection of information stored on a distant, two-dimensional surface. This concept is analogous to a hologram, where a two-dimensional image encodes a three-dimensional object. To understand how this principle could apply to the entire universe, we need to delve into the realm of string theory, a theoretical framework that attempts to reconcile general relativity, which describes gravity, with quantum mechanics, which governs the behavior of particles at the smallest scales. String theory posits that the fundamental constituents of the universe are not point-like particles but tiny, vibrating strings. These strings can exist in multiple dimensions, and their vibrations give rise to the various particles and forces we observe. One of the most significant developments in string theory came in 1997 when physicist Juan Maldacena proposed the anti-de Sitter/conformal field theory, ADS/CFT, correspondence, also known as the holographic duality. Maldacena's conjecture provided a concrete realization of the holographic principle. He showed that a type of string theory defined in a higher dimensional space, AD space, could be equivalent to a quantum field theory defined on the boundary of that space, a lower dimensional surface. This duality suggested that the behavior of gravity in the higher dimensional space could be fully described by the quantum field theory on the lower dimensional boundary. Maldacena's work provided a powerful tool for physicists to study quantum gravity and other aspects of fundamental physics. It showed that complex problems in higher dimensional spaces could be translated into more manageable problems in lower dimensional spaces. This duality has since been used to gain insights into black holes, particle physics, and even condensed matter systems. The implications of the holographic principle extend far beyond black holes and string theory. If our universe is indeed a hologram, it could revolutionize our understanding of space, time, and reality itself. One of the most profound consequences of the holographic principle is the idea that the fabric of spacetime is emergent rather than fundamental. In this view, spacetime and gravity arise from more basic, underlying information encoded on a two-dimensional surface. This perspective challenges the traditional notions of space and time that have been central to physics since the days of Isaac Newton and Albert Einstein. In Einstein's theory of general relativity, gravity is described as the curvature of spacetime caused by the presence of mass and energy. However, if spacetime itself is emergent, then gravity may also be a secondary phenomenon arising from more fundamental processes. The idea of emergent spacetime has led to new approaches in the quest for a theory of quantum gravity, a long-sought goal in theoretical physics. Quantum gravity aims to reconcile the principles of quantum mechanics with general relativity, providing a unified description of all the fundamental forces in nature. The holographic principle offers a promising framework for this endeavor, suggesting that gravity and spacetime may emerge from the quantum entanglement of information on a lower dimensional surface. Quantum entanglement is a phenomenon where particles become interconnected in such a way that the state of one particle cannot be described independently of the state of another, regardless of the distance between them. Recent research has shown that the structure of spacetime itself can be related to patterns of quantum entanglement. In this view, the geometry of spacetime emerges from the entanglement of information on a lower dimensional surface, consistent with the holographic principle. The holographic principle also has implications for our understanding of the universe's origins and the nature of the Big Bang. In traditional cosmology, the Big Bang is thought to be the moment when the universe expanded from an extremely hot and dense state into its current form. However, if the universe is a hologram, then the information that gives rise to our three-dimensional world may have been encoded on a two-dimensional surface from the very beginning. This perspective could provide new insights into the nature of the early universe and the processes that led to its expansion. One of the intriguing aspects of the holographic principle is its potential to explain the mysterious nature of dark energy and dark matter. Dark energy is the unknown force driving the accelerated expansion of the universe, while dark matter is the unseen substance that makes up most of the universe's mass. If our universe is a hologram, then dark energy and dark matter may be manifestations of underlying information encoded on a two-dimensional surface. This idea could lead to new ways of understanding and detecting these elusive phenomena. Despite its revolutionary potential, the holographic principle remains a highly speculative and theoretical concept. It has yet to be directly tested or observed in experiments, and many questions about its validity and implications remain unanswered. However, ongoing research in theoretical physics, cosmology, and quantum gravity continues to explore the possibilities opened up by this idea. One of the major challenges in testing the holographic principle is the lack of direct observational evidence. Because the principle suggests that our three-dimensional universe is a projection of information on a two-dimensional surface, any direct observations we make are also part of this projection. As a result, detecting the underlying two-dimensional structure is incredibly difficult. However, some physicists have proposed indirect methods for testing the holographic principle. One approach involves studying the cosmic microwave background, CMB, radiation, the afterglow of the Big Bang. The CMB provides a snapshot of the early universe, and its patterns could contain clues about the underlying holographic nature of the cosmos. By analyzing the CMB with high precision, scientists hope to detect subtle deviations that could indicate the presence of a two-dimensional structure. Another approach involves the study of black holes and their properties. Black holes are natural laboratories for testing the holographic principle, as their event horizons are the surfaces on which information is believed to be encoded. Observations of black hole mergers, gravitational waves, and other astrophysical phenomena could provide indirect evidence for the holographic nature of the universe. In recent years, advancements in technology and observational techniques have opened up new possibilities for exploring the holographic principle. The development of next-generation telescopes, such as the James Webb Space Telescope and the Square Kilometre Array, promises to provide unprecedented views of the universe. These instruments will enable scientists to study the CMB, black holes, and other cosmic phenomena with greater precision, potentially uncovering evidence for the holographic nature of reality. In addition to observational approaches, theoretical physicists continue to develop mathematical models and simulations to explore the implications of the holographic principle. These models aim to understand how the information on a two-dimensional surface gives rise to the three-dimensional universe we experience. By refining these models and comparing them to observational data, scientists hope to gain deeper insights into the nature of the cosmos. The holographic principle has also inspired interdisciplinary research, bringing together physicists, mathematicians, and computer scientists to explore its implications. One exciting area of research involves the use of quantum computers to simulate holographic systems. Quantum computers, which leverage the principles of quantum mechanics, have the potential to model complex systems that are beyond the reach of classical computers. By simulating holographic systems, researchers hope to gain new insights into the nature of spacetime, gravity, and quantum entanglement. The holographic principle's influence extends beyond the realm of theoretical physics and into popular culture and philosophy. The idea that our universe could be a hologram has captured the imagination of the public and has been featured in numerous books, movies, and television shows. This concept raises profound philosophical questions about the nature of reality. If our universe is indeed a hologram, it challenges our understanding of existence, perception, and the very fabric of reality. Are we merely projections of information on a distant surface? How does this affect our notions of identity and consciousness? These questions push the boundaries of both science and philosophy, inviting us to rethink the nature of the universe and our relationship to it. Whether it ultimately proves to be a fundamental aspect of reality or a stepping stone to even deeper truths, the principle exemplifies the bold, innovative thinking that drives scientific progress. It reminds us that our universe, with all its mysteries and complexities, is still a vast, uncharted territory, inviting us to explore, question, and discover. In the end, the holographic principle is more than just a scientific theory. It is a journey into the unknown, a reflection of humanity's relentless curiosity and desire to understand the cosmos. As we continue to unravel the mysteries of the universe, we may one day find that our three-dimensional world is indeed a projection, a hologram of information on a distant, two-dimensional surface. Until then, the holographic principle remains a fascinating and profound idea, one that challenges us to see the universe in a new light and to ponder the true nature of reality.